let me go over the whole thing again. So at Data Cabinet, we are trying to build, so just a quick introduction. We are trying to build a platform for deep learning and machine learning. And we have a product out there where you can maintain your notebooks and their programming environments, and you can share it between people. And then and you can use languages like R, Python, and others as well as. So here for this lecture, we will go through the topic of regularization, and you can please ask questions here. After every slide, we'll check questions, and if you have any technical, please sign up for Data Cabinet, and you can access these notebooks. And if you have any trouble, then we can help you on the chat. And okay, we'll get started. Sorry about the muting. All right. So let's start with how we can think about, like, what are the ways, the higher level ways of modeling machine learning problems. So in a machine learning problem, you are given some data points. So for example, here you are given age, height, and education, and you're trying to predict the income of a person. And so you could treat it as modeling a function y is equal to fx plus epsilon, where x comprises of x1, x2, and x3. And epsilon is basically what is not captured by x1, x2, and x3. So epsilon is anything else. So for example, it could be your where you live, which is not captured by these factors. So that is one way to think about how we model a machine learning model from data points. Another way would be to think of a machine learning problem would be to figure out or assume a probability distribution. So given like these, we think of these data points as coming from this probability distribution. So let's suppose you are given a probability distribution that for a particular age, particular income, particular education, this is the probability distribution. It has a mean of, let's suppose it's a normal distribution. It has a mean of $50,000. It has a standard deviation of $10,000, and you get, so that is kind of the probability distribution that we model these problems for. And sometimes we also assume these probability distributions just to get an intuition of theoretical results. And test data or training data could be considered as a sample from this probability distribution. So I hope everything is okay. If you have any questions, please let us know. Okay. All right, we'll go to the next slide now, and go to the next slide now. And okay, so let's try quality of the fit. So what is so once you fit a model, how good does it behave on test data? How do you even get a feel of how it will do on the test data? You will have to get a metric around how well your model is performing. So one way to do that would be just get, for test data, you get the answers that your model gives and get the actual answers, subtract them, square them, and take a mean of all those values for the new test points. So this will give you a metric of how well your model is doing. And and what we can do is we can produce a number of different models, and then we can do the same. We can get this same metric for all these models and see which one performs the best. So this is one way to think about how we can get the best test error. We can choose a model that gives the best test error. And something like this happens when you do cross-validation or other techniques. So one problem here would be, how do we generate these multiple methods? So one way to do it could be to increase the flexibility of the model. So what is the flexibility of the model? So flexibility of the model, one way to think about it is the polynomial degree of the model. So think about this yellow line. This yellow line is a linear model. It has just degree of freedom 1, let's suppose. And this black line is the actual probability distribution. So we are assuming a probability distribution here. This yellow line is a linear fit for the data points. Then this green line, let's suppose, is a degree 16 fit for this data points. And this so this has a much higher flexibility. So now we can plot how, on increasing flexibility, your model test error and training error behave. So as you increase the flexibility of a model, or you increase the polynomial degree of the model that you're fitting, then the training error definitely keeps going down, because you can fit all the points. So if you see this green one fits these points much better. So training error has to go down. But what we see is that the test error actually starts going up after a while. So so this green point on the right picture is called an overfit model, where the training error is low, but the test error is going high. This brown square points on the left, they can be considered as underfitted model, where the model capacity is not high enough that it can predict it well. And this blue square is where the perfect model is. So that's what we are trying to get to. So let's get to any questions, if there are any questions. All right, we'll go to the next slide. So one of the central results around this, let me go back to the notebook here because the slide is not good, is bias-variance theorem trade-off. So this is a theoretical result. I'll try to give an intuition behind it and see. So let's suppose you fit. So bias-variance trade-off. This is the formula. So given y is equal to fx plus epsilon, this is so the expected value of so let's suppose we are given a sample set. We are given a set of sample points, and we are trying to fit a linear regression or a neural network onto it. What we do is we sample points from within the test set, training set, and we fit linear regressions on all those samples. And we will get different linear classifiers, right, or different neural networks. And for all these neural networks, we are taking a test point, y naught, x naught, and we are using all these neural networks to get the value. So fx naught. So fx naught is basically the neural network applied to x naught, and or the linear model applied to x naught. So again, the setup is something like this. We take a number of training points. We take a number of samples from the training point, we fit like one classifier, either neural net or linear classifier, on all of these different samples that we got. And then we take this linear classifier and these linear classifiers, and then we try to try to predict what will be the value of y for x naught, and then we try to get the mean square error of expectation of square error of this value. Now, what will this be? Now, theoretically, this can be proven to be variation of fx naught. So how much variation, like if you choose the data points, how much difference does it make in the model? So for example, if you change the data point, a low capacity model like linear regression will not change that much. But if you change like the data, then a neural network might change a lot. And this a bias. So a bias is a term where how much error is there, or how much bias is there in every prediction. So for a linear model, this number will be higher, because if the original data is very complex, it has complex dependencies, a linear model cannot capture it, then it will do a lot of errors every time. But a higher capacity model will not do a lot of errors every time. So first term is variance, which is how much for the same model, how much do the outputs differ. The second term is bias, which is how much error does that particular method do? Like how much does linear regression, how much error does it cause? So this result says that the variance plus bias is what the expected value of this test error will be. So now, if you think about it, a higher capacity model will have low bias. Higher capacity model or higher flexibility model will have low bias, but it will have a higher variance, because it will fit like a new model for every set of data. But a low capacity model will have low variance, but it will not but higher bias. So our goal here is to find a good trade-off between the two, where the variance and bias sum to the minimum error. So this is the error that we are trying to minimize. So if you think about it, in these pictures, which give you a good idea of what it is, there is the left side is all these models go up in flexibility, and this green line or blue line is basically the variance. It's the bias, and this keeps going down, but the variance starts going up. And if you see, the mean square error is this red line, which actually has this U shape, which is very common. And this U shape, there is a minimum point that we're trying to fit. So in the leftmost figure, the optimum point is around the flexibility of 6. So in this figure, in this figure, if the optimum point is around 1, and it also depends on the original. If you think of the training set has come from an original probability distribution, then then you can also think of it as coming from a like 6 as the 6 as something close to the original probability distribution, or here like 4 as the flexibility of 4 as something close to the original probability distribution. So let's see if there are any questions. Are there any questions on bias-variance trade-off? This is like one of the very important results to understand and how regularization works. So variance and bias. This is all a play of variance and bias. So I'm not able to see the questions or comments, if there are any. Let me see if I'm... 1 second, let me check. One second. Okay, let's get back. So now let's go to regularization. So what is regularization? So ideally, like we saw in bias-variance trade-off, we would try to find the optimum point, which is this point, for to minimize the test error. But so regularization is a way in which we try to reduce the variance, but not increase the bias too much. So what we do is we put constraints around different things, or we do different techniques, so that the variance of we take a higher model like neural network. We put we try to bring the variance down, and not affecting the bias too much, and that's what regularization is. And so the, so there are multiple ways of doing it. One way could be to put restrictions on parameter values, that they should be less than this value, or in the objective function, instead of mean square error objective function, we can add like a penalty to it, if that reduces the variance um, of the classifier that we produce. So using these, we can get better test case performance. And also, using this, you can take like a very high capacity model like neural network, and control its variance, and get a good neural network. So let's go to this new notebook, which kind of talks about bias and variance. So we will. This is a very important concept, so I wanted to go through it a little bit more. Okay, so here in this notebook, what we are doing is this is the original distribution. We are assuming that this is a signed distribution, and then we are sampling from the signed distribution by adding a Gaussian. We are trying to fit multiple polynomials to it. So for example, here we are trying to fit an 8-degree polynomial into it. And now we are trying to fit multiple polynomials into this. So there are like multiple degree. We're trying to sample differently and fit a 4-degree polynomial always into it. So if you see, the 4-degree polynomial seems to have a similar shape. So now we are so now if you see, and you can do it in code, that if you take you can actually get the bias and variance on a new point, and you can see that the bias goes down as you increase the flexibility. So here we are doing, if you see, we are doing max degree of 15. So we are doing we are changing the degree from 1 to max degree, and then the bias keeps going down, the variance keeps going higher, and then the error, which is this green line, it kind of again has this U shape. So this is kind of, you can do it in code if and see. We have the notebook online. So also let's see if so now let's go to norm penalties. So go back to slideshow. Okay. Any questions? Okay. Norm penalties. So how do you? So norm is basically norm is, so L1 norm, for example, is the absolute value of all the theta or weights are the same thing, and you take the absolute value of all of them. You raise, you can add them together and average them, or you can raise them to a power and then take a corresponding. So if you raise them to a power 2, then you take a square root. You raise them to a power, absolute values, add them together, take a square root. So that is L2 norm. L1 norm is just take the absolute values, add them together, and average them. And then L3 norm is take the absolute value, cube it, add them together, and then take a cube root of it. So now if you see what you can do is you can take these weights and add a norm penalty to the cost function. You take the cost function, you add and alpha is a hyperparameter. You just choose it and see how it behaves, and then you take this norm penalty. So this is one way of doing regularization. So given an alpha and this function, it will have a certain feature, it will behave in a certain way. So for example, in L1 regularization, features will be chosen in a different way. We'll come to that than L2 regularization. But they will all have the effect of reducing variance, because they are trying to limit the amount of theta that can give a good cost function, that can give a low cost function. So also that for neural networks, we have weights and biases, like we saw in the last video, and but we do not really put norm penalties on the biases, because biases don't contribute that much to the classifier, and it doesn't cause so much variance. So we don't regularize the bias. Also, for neural networks, you could use a separate. The book says you could use a separate alpha, because alpha is a hyperparameter for every layer, or you could use the same alpha. So yeah, so that's how parameter norm penalties are used. So let's go to one parameter norm penalty, that is, and see how it behaves. So L2 regularization, which is basically the square and square root way of doing regularization. So in this one, you could also see. So for simplicity, we are taking just the weights, not the biases, and we are trying. We take the original cost function, which could be anything, which could be like a mean square or anything else, and then we add a penalty, which is hyperparameter alpha multiplied by the squares of all the weights. So now let's see how this will behave. So how does this actually cause regularization? So the gradient of this right-hand term would be the gradient of the original function plus alpha multiplied by w term. So every square, the 2 will go away because it's a square. The 2w will cancel the 2s, and we'll just have an alpha multiplied by w. Now, if you're doing a stochastic gradient descent in which you're trying to optimize J by going a little towards the negative gradient, then you will take a step towards in the epsilon step towards this new gradient, right? And if you rearrange this, then you will get this 1 minus epsilon alpha w minus epsilon of the original function. So we will have basically a small, so it will be basically going in the same direction as if there was no regularization, but every time the weight will be penalized a little bit. So that's fine. Every time doesn't matter so much. What matters is how it behaves in the end, right? Like how will it at the end, what will be the effect on W? So let's try to figure that out. So we'll make some make some assumptions just to get an intuition of what will happen at the end because of L2 regularization. So if we assume that the cost function is so one assumption is that the cost function is quadratic. So you can write it something like this, where h is the so it's a quadratic function in W. And now let's see. So if you so now let's try to, if the cost function is quadratic, right, and W star is the minimum of the original cost function without regularization. So without regularization, if you try to find the minimum weights, you will get W star. Now you assume that the cost function J is quadratic in W. Now we are trying to do, what we do is we do a Taylor series. Now because to find the value of this function at any W. So so what we do is of this function which has the regularization term. So W star is without the regularization term. Now we tried to model this function which has the regular J bar W, which has the regularization term, and get its value for any W. So this will be J W star, the minimum point, plus the first derivative. And what is the first derivative at W star for JW? It's 0. All right. So we can forego the first derivative. Now the second derivative, which is the Hessian of this W, we take that and we multiply it with half of W minus W star. So if you see, because it's a you can see it that because it's a quadratic in W and W star, it can be thought of as and W star is the minimum point. You can think of it as if in 2 dimensions, you can think of it as a line, like a parabola with a minimum point, and then you are trying to get the value at any W, and then you get this W minus W star H W minus W star. Because this is the second order term, and because we are assuming that this is a quadratic function, there will be no third order term. The third order derivative will be all 0. So now we go. So we can also see that because W star is the minimum point, right? So if you see J bar W will be always greater than JW bar, JW star, because this is like the unconstrained minimum point. Now, because of that, all these values for any W will be positive. For any W, this value will be positive, which means this will be a positive semi-definite matrix which has all positive eigenvalues. So all positive or 0 eigenvalues. And now let's do a derivative of this J bar W. So if you do a derivative of this J bar W, then you only get this J, because W star is constant, so there will be no term for that. Now you will get H W minus W star equal to 0. Oh wait. Oh, sorry. No, this is also, sorry. This does not, I think I said this consists of the regularization term. This does not consist of the regularization term. That is why this J bar W. So now we get for the to minimize this, all we have to do is to H W minus W star is equal to 0. And if we actually had the regularization term in this function, then the equation would change as H W minus W star plus alpha W is equal to 0. Now, now if you rearrange this in an H, as we said, is a positive semi-definite matrix, so it can be written as Q sigma Q transpose where sigma is a diagonal matrix, and you have all the eigenvectors in Q. And then what we can do is, if you write this equation properly, you can get a W optimal as Q sigma plus alpha I inverse. You can get this value, which and if you see, if alpha is 0, then this will come to W star again. So what is this doing to W star? What this is doing is it is actually taking W star to the coordinates of to the coordinates of the eigenvectors. Then it's expanding it by on every direction by alpha, and then bringing it back to the original dimension. So if you think about it, like the dimensions that had high eigenvalues, they won't be affected that much. But if you see the low eigenvalues, then they will be shrunk that much because of this inverse in that direction. So another way to see is every direction will be shrunk. If the original eigenvector was lambda I, then it will become lambda I divided by lambda I plus alpha. So then it will be a smaller value. So this will impact the lower eigenvalue directions more than it will impact the higher eigenvalue directions. So it will, in effect, it will shrink the lower eigenvalues by a lot, and not the higher eigenvalues by that much. So another way to think of it in a picture, which is always nicer. Let me see if there are any questions. Okay, so another way to think of it is in this way, where you have contours for the cost function as well as contours for the regularization function. So this is the contours for the regularization, and this is the contours for the cost function. And let's see if I'll come to the sources. Sources are listed below in the notebook, so you can see where the images are from. Yeah, Alex and I built this together. So if you have any questions, I'll wait and Alex can answer. I'm not able to see the chats for some reason. Okay, so let's go here, and in this one, let's let's suppose in this one, these contours, the dashed contours, are the contours for regularization functions, the equal values. So each contour is basically equal value of regularization function, L2 regularization function, and this is the actual cost function. Let's suppose the one above. So if you see, it will hit somewhere in W bar, right? Because it has to be in a point where they just intersect, because otherwise you could move them around and get like a smaller value of the cost function. But here, if you see, the x direction got shrunk by a lot, but the y direction didn't get shrunk by a lot. And one way to explain this is, like, if you see W1 and I should not call x, y direction, I should call W1 direction and W2 direction. So W2 direction got shrunk by a lot, but W1 direction got shrunk by a lot, but W2 direction didn't get shrunk by a lot. So W star was the original best. Now W bar is the original best. W1 has shrunk by a lot. W2 has not shrunk by a lot. And this is because In the W2 direction, there is a lot of gradient because the contours are moving very fast. So the Hessian is also has a higher eigenvector in this direction. But in this direction, the contours are not moving very fast. So the Hessian doesn't have a big eigenvector in this direction. So you can think of it this way. So let's come back to L1 regularization. So in L1 regularization, instead of doing a square and penalties, we just do absolute value penalties and we just add them together. And if we do a very similar analysis to similar analysis to what we did for L2 regularization, then we define this new function as alpha multiplied by the absolute value of W. Now the derivative of this would be alpha multiplied by the sine of W, because it won't be alpha multiplied by W itself. So this, but then we are more interested in how it affects the final outcome, right? So for this, we'll make another assumption. So in the L2 regularization modeling, the assumption was that the cost function is quadratic in W. We'll make another assumption here that the Hessian is also is a diagonal matrix. So the Hessian. So if all the features, all the W's are like not related to each other, then Hessian could be a quadratic could be a diagonal matrix. And so we will do, we'll not go into the details, but if we do the same trick that we did for L2 regularization, the Taylor series trick, derivative trick, then the JW comes out to be JW star plus this value, the alpha WI plus half into HII multiplied by W, the squares of all the differences. And the analytical solution for the optimum value of Wi is the sine of Wi multiplied by the max of 0 and Wi minus alpha divided by the Hessian of the ith value. So so this has a little interesting property that either it does feature selection. So if Wi star minus this alpha divided by HII, so if but think is positive, is negative, then there should be no positive. I don't think there is a I think I wrote it wrongly. I don't think there's absolute value sign here. So it's either 0 or it's 0 if I should remove it. Wait. So it's either if the Wi is too small, it just puts it to 0. If the Wi is big enough that it's a positive value, then it actually puts then it actually picks them. But it scales it. It perturbs it by a amount alpha divided by HII. So you can think of it as it does not scale the Wi's. It moves the Wi's, or either puts it to 0. So it can also be thought of doing some feature selection. So if you are doing it's basically putting some Wi's don't matter at all. So if you do L2 regularization, then some of the and if you try to fit a linear regression, then some of the features will not mean anything. So that's sorry, L1 regularization. So another way to remember this and think about this is to see these contour plots. So the absolute value function is this blue tilted square, and these are the contours for it. Contours, I mean equal valued points. And if you take like a contour for the loss function, which is something like these concentric circles, then they are going to meet this particular this particular square at a corner point, because if they don't meet at a corner point, then you can shrink the if for example there was a bigger concentric circle that was not meeting it at a corner point, and you could just take a smaller concentric circle which meets at a corner point. So what this means is it does a feature selection. So beta 1 actually is pushed to 0, where and so then only beta 2 matters. So this does a feature selection, but that's not the case if your contours are circular. So for example, and in the L2 regularization case, the contours are circular, so it does not do feature selection. It shrinks everything. It takes it into its eigens, into its eigenspace of the Hessian, and then shrinks it by particular amounts, and then brings it back to the original domain. So that's the intuition behind these two. So there are other ways to look at this as well. There is another way to look at what L1 and L2 regularization are doing. So if you model the same problem in a different way, that there is this Lagrange function which takes a constraint and a coefficient. It takes and tries to optimize any function. So given our loss function, original loss function, J, which could be like a mean squared loss, we add this term, a coefficient, and then a constraint. So this, for example, here, the constraint should be that this function, this omega function, which could be L2 or L1, is less than k. So if it's greater than k, then it will start adding a lot to this function. So what this alpha and k do is they try to bring the non-penalties below this value, below k value, and this can be solved using gradient descent methods. This kind of formulation, a Lagrange function formulation, can be solved using SGD. And so if you see the theta star, that the optimum theta that comes is the argument of this loss, this L function, the Lagrange function. And so if you also think of like a fixed k and theta, alpha, fixed k and alpha, then this problem becomes basically same as a regularization function. If because k term k is fixed, so this need not be optimized. Alpha is also alpha is fixed, so this becomes a L2 or L1 regularization function. So another way to think of L2 or L1 regularization function is that we are trying to shrink the area area to be within k. We are trying to shift this L2 regularization function to be within k. And in fact, sometimes this k can even be found given the function. So that's what norm penalty. That's how it can be thought of in the constrained optimization ways. So instead of thinking of it as adding a particular value to the loss function and optimizing it, you can also think of it as like trying to put a constraint on the coefficients. So using that, we could do something better using that. So what we can do is what we can do is so instead of using like trying to optimize the original cost function with a non-penalty, what we can do is we can take out the non-penalty, and we can just try to optimize the original cost function using some gradient descent kind of method. And at every step, what we do is, if it violates the constraint, then we do take a projection to a point where it does not violate that constraint. So this process can have a lot of advantages. So one advantage is that, let's suppose we already know that the coefficients satisfy this constraint and it cannot go beyond k in some models, then we can use that directly. Or if the non-penalty is such that it makes the original function very non-convex, then and it always gets stuck in a local minimum, then we can use this method. Or if if we use high learning rates, what can happen is like the original norm-based function could lead to very high coefficients very soon and could lead to numerical instability if the gradients are high in certain directions. So then this method can be used to keep them in check. Like, here the coefficients always have to satisfy that constraint. So it can be like, it can not do numerical errors. So I'll give it a minute. I cannot see questions, so I'll give it a half a minute to for Alex to take any questions. Something is wrong with my, as you can see, my screen. It cannot do, cannot see the questions. Let me see if I can see it here. Okay. All right, let's go to yeah, the notebook is shared. The ID is on the email. So I can share it again. I'll share it again. I made some changes today, so I'll share it again. And so let's go to yeah. So consider. So also regularization is very useful in underdetermined problems. So underdetermined problems. So for example, one problem that I remember is that you're given, you can only collect data for 10 people, but there are like 2,000 genes that are involved in determining a lot of things. And you want to figure out whether this person is has some genetic defect or not. And you are only given 5 data points. So you can, it's very it's an underdetermined problem because there are too many features. Now if you take a x transpose x of that, so a lot of methods, like which are the most important components, of these features that can tell you you can use for a future prediction. These methods require you to produce a singular like an invertible matrix, but you cannot. So you can think of, but when you add a regularization term, so instead of trying to do a PCA on principal components of trying to find the principal components of the original matrix, or the original matrix's square form, we can try to find it we can add a alpha I term to it and then make it invertible and then work on that. And those kind of tricks can also work on it's basically something like you're also imposing a condition that not only do the W's so of these genes have to satisfy all the 5 data points that I have, they should also be less than a particular k. So if you put that extra constraint in that, then it becomes actually solvable. So it can be used for underdetermined problems. And also in some problems like logistic regression, if you have totally linearly separable classes, and if you're trying to run a logistic regression on it, then you'll get you'll get a vector that does it fine, like W vector. Then 2 multiplied by W vector could also do it well. And the numerical method will get stuck. If you are trying to do SGD, it will keep going and overflow at some point. So if you add a regularization term to the cost function of this logistic regression, then it can actually give you an answer. It will also satisfy a constraint, but it will give you an answer. So that's so regularization is useful in that way as well. So so data augmentation. So data augmentation. The trick here is that you're in some domains, like you can only have so much data. Then but you want to train a classifier that is more that can do better on test data. What you do is you fake data, which can be like, so if you are given an image, you rotate the image. If you're given an image, you take a mirror image of the image and then feed it to the same classifier. And of course, you have to take care of transformations that change the class of the problem itself, like D becoming a B or 6 becoming a 9, and you have to take care of that. And speech recognition also, you can fake data in certain ways. So this technique is called data augmentation. And also a form of data augmentation is putting noise into your inputs or into your hidden units. So if you make a neural net on just some input, then it might not be very it might be susceptible to noise. But if you make sure that the noise is if you make sure that the noise is less, then if you make sure that the noise goes in the training phase itself, you induce some extra noise, then it becomes more less likely to do badly on test data with noise. So that is also a form of data augmentation, and it can be done on both input layer as well as on the hidden units. So hidden units also are trying to get some feature out, and then the feature, it can be done on that level as well. So the Ian Goodfellow, his book notes that data augmentation should be taken into account, like before you compare two algorithms. So if one algorithm gives a 3% error rate on certain data set, and then another algorithm gives a 2% data set on an augmented data set, then you don't want to keep the 3%. You don't want to just say that the 2% one is better than the 3% one, because the 2% one got better augmented data. Also, that sometimes some algorithms might be naturally not susceptible to noise, because they make sure that they account for Gaussian noise inside of the algorithm itself. So data augmentation, usually data augmentation is considered to be the techniques that are domain specific. So for speech specific or image specific, they're not like, if you add a Gaussian, if it's something more generic, like adding a Gaussian, it could also be part of the algorithm itself. So let's go back and do. So we will. This is the. So noise robustness. So noise applied to input and hidden units, right? Like we were discussing, is a form of data augmentation. But there is another form of noise robustness. But the noise could be applied to the weight itself. So we can apply the noise to the weights, and so let's suppose we are trying. This is our cost function, which is like the expected value of y bar x, our model output, minus the actual output, actual test output squared, and we are trying to take expected value of it on given the probability distribution. Now instead of doing this, what we will do is in the model, we'll perturb the weights by a little bit, and we'll perturb it by a normal and a mu which has like a constant covariance matrix, like a identity covariance matrix. And now, if we perturb the weights by this EW, then if we try to get the same value, same cost value, then it will be something like this formulation is just is just a squaring of the internal terms. But the interesting result is that it acts as the original term plus a regularization term, which is determined by this nu and a derivative of the model weights, the derivative of the model output with respect to weights. So what this means is that if we are regularizing on this value, so we are trying to keep them within a bound. So by doing that, we make sure that the derivative of weights with respect to the output is not that high, which makes sure that the output that we'll find, even if you change the weights a little bit, it will not be too bad. It will still be the same classifier. So it actually makes it better, makes the weights more stable. So it's not like if you perturb the weight by a little bit, it will go too haywire. So we will cover the rest. So these were the topics we wanted to cover this time. We'll cover a bunch of other ones like dropout in the next class. But we encourage you to go through this and also go through the bias variance one, the notebook. We took it from somewhere, but it's very important to understand this bias variance and then understand the L1, L2 regularization from that angle, and also yeah, and these results are very interesting. These pictures are a good way to remember these. If you remember these pictures, these are a good legends to remember all these results. So yeah, let's see if we have any questions. Sorry, my chat is somehow not working, but I'll try again. Oh, actually, I can just go to YouTube and look at it as well. So oh, I could have just. Oh, I'm really sorry for all the this mess. If you have any questions, we can see it now. Okay, if there are none, then we'll close it. And sorry for all the problems with this with the questions and with the muting. We'll make sure these won't happen. We'll do another round on regularization, and hope to see you there. It's written in the. Let me show you. It's written in the notebooks. So there are three main. Not this one. This one. There are three main places I took it from. One is this book, Introduction to Statistical Learning, by these people. They are Stanford professors, and of course the Deep Learning book by Ian Goodfellow, and the bias and variance. The bias and variance notebook I took from the internet, but it's very nicely written, and you can look at it on Data Cabinet. Yeah, the Data Cabinet notebook ID is in the email, so you can just get it from there. And if you can take Data Cabinet for a spin and give us some feedback, that would be great. And if it works very well and you can use it for your own presentations or for your own work. It's free for the first 3 months, so you can just use it. It comes with a 4 gig memory cloud machine, so it gives you a lot of compute resources. Did you sign up to code? It will send you an email if you signed up on. It will send you an email. It provisions your hard drive, and it takes like 5-10 minutes for it to do everything, and then it will send you an email once your account is ready. And if you do your own presentations or events, you can use us, or it's very useful in sharing your notebooks and full programming environment. So you should try that out. Sure. Let me share that with you. Actually, sent it an email somewhere. So you can get the final email here. We'll be also sending out a survey shortly. So if you have any comments, and sorry for today's fiasco about the muting, it was a big lesson. All right. If you don't have any further questions, please, if you have any comments, any feedback, please write to us. And we are available at info@datacabinet.systems. And thank you for joining us, and we'll sign off for now.